Hello, AP Chemistry. How are we doing today? Hopefully, y'all are doing well. So today we are going to be continuing our notes on acids and bases. So continuing into the acid and base unit. Today we are going to be continuing into acids. Specifically, we're going to go into part 2 of our acids, specifically focusing on how we work with weak acids in terms of pH. All right. So let's look at calculating the pH of a weak acid solution. So basically, all this involves is setting up an equilibrium expression. So basically, you're going to be using your Rice table. All right. So here it says calculate the pH of a 0.100 molar solution of acetic acid. The Ka of acetic acid is 1.8 times 10 to the negative 5. So again, we're setting up a Rice table. So we've got our reaction, the initial, the change, and then basically what our final is going to be here. So our reaction is we've got some acetic acid, which is HC2H3O2. And it is in a solution, so we can add our water here. Now remember, water is a liquid. The acetic acid is aqueous. And in our reversible reaction, we're going to produce that hydronium ion and acetate. Okay, so in our initial, I have 0.100 molar of the acetic acid. Water is a liquid, so we know we're not going to use it at all. We've got our hydronium, which we're going to have an initial of 0, and our acetate is an initial of 0. The change, minus x plus x. So our final here is going to be 0.100 molar minus x. And then for the hydronium, it's just x, and the acetate is just x. Okay, now I need to actually write out my equilibrium expression. So I have Ka equals the concentration of H3O plus times the concentration of C2H3O2 minus over my concentration of HC2H3O2. I have my Ka equaling 1.8 times 10 to the negative 5. And we do need to realize that that is a small Ka, which we know that that means we can assume that something is negligible here in a little bit. So then that equals x squared over 1.00 minus x. Now again, we knew that our Ka is a small value there, so we can make the assumption that x is negligible here, so we can get rid of that. So now we would just go ahead and solve. So 1.8 times 10 to the negative 5. Sorry, this should be 0.100. So then times 0.100 equals x squared. And then we're going to square root both sides. So then we take the square root of 1.8 times 10 to the negative 5 times 0.100. And that's going to give me my x value. So what I found is that my x equals 1.34 times 10 to the negative 3. Now, that is not it, because it doesn't ask me for my x value. It asks me for the pH. So basically, all I would then do is I know that this x value is the concentration of my hydronium here. Let me highlight that for you. So my x value is my concentration of hydronium, right? Because we've got a final of x there. So I know my concentration. So to solve for my pH, I know that pH equals the negative log of my concentration, 1.34 times 10 to the negative 3. And so I plug that into my calculator, and I find that my pH equals 2.87. And then there would be my final answer. All right. So this next one is a little bit different, but I do actually want y'all to go ahead and give this one a try. I'll work it out later, but I do want you to give it a try without me walking you through it. So go ahead, pause your video, solve this problem, and then come back to it, and I will show you how to do it. All right. All right, so here is what you should have ended up doing. So the very first thing you should have done is write out your Rice table. Now, the next thing is we're solving for our Ka value, which means we're going to need to know what X is. We need to know what that concentration is. To find that, basically we can take our pH and we take that and take 10 and raise it to the power of whatever our pH is, the negative version of that. So I have 10 to the negative 5.25, and that gives me my hydrogen or hydronium concentration, which is 5.6 times 10 to the negative 6. Then what I do after I've written out my Ka expression, then I can go ahead and plug in my value. So over here I highlighted. So I know my X value is that 5.6 times 10 to the negative 6. So I plugged it in, and then I solved for my Ka, which wound up being 3.1 times 10 to the negative 10. Okay? All right. So now that we've got an idea of how to calculate the pH of a weak acid solution, let's take a look at how would I determine the percent dissociation. So basically, what percentage of that weak acid actually separated out? Because with a strong acid, we're going to make the assumption that it's 100% dissociation, right? With a weak acid, we can't make that assumption. Because as we work with those weak acids, yes, it will dissociate some, but not completely. And so we do need to keep that in mind. That's why we actually have to use our equilibrium expressions to solve for that pH, for example. Okay. So what do I need to do? Well, for determining the percent dissociation for a weak acid, basically what we're going to do is we're going to take the amount dissociated divided by our initial concentration. So we're going to still use a Rice table to solve for that that X value, that concentration. And then once we've done that, we're going to take part over whole, essentially. That final concentration divided by that initial concentration times 100. All right, so right here, calculate the percent dissociation of 1.00 molar HC2H3O2 solution with a Ka of 1.8 times 10 to the negative 5. Now, one thing to note is for a weak acid, percent dissociation is going to increase as the acid becomes more dilute. So basically, we're going to see that equilibrium start to shift to that right side. All right. So again, calculate this percent dissociation. So I've got my Rice table. So first off, my reaction, we've got our acetic acid. And we're just going to do a shortcut because we don't necessarily need to write the water there. But if we don't write that water, then we do need to recognize that it's the hydrogen ion plus, sorry, not concentration, hydrogen ion plus C2H3O2 minus. So the initial concentration here is 1.00. There is no hydrogen or acetate concentration, minus X plus X. So then we have 1.00 minus X, X, and X. Now, let's go ahead and solve this. So I find my Ka equals the hydrogen concentration times the acetate concentration over the concentration of the acetic acid So 1.8 times 10 to the negative 5 equals X squared over 1.00 minus X. Again, we can make the assumption that that is negligible. So then I would work this out, take the square root of 1.8 times 10 to the negative 5 and I'll find that my x value equals 0.0042. So that would be my x value. That would be that concentration there. So now I know my final concentration. So then I would take the final concentration, so 0.0042 over the initial concentration, 1, times 100, and we'll find that we had a percent dissociation of 0.42%. And that would be it. Okay, so now we are going to go ahead and move on. So determination of pH of a mixture of weak acids. Now this is basically just a kind of, I'm going to talk you through it. So all that we need to take into account when we're mixing multiple acids is whichever has the largest Ka value, because it's going to be the one that is going to contribute the greatest concentration of hydrogen. And so essentially it's the only thing we need to take into account. So if you mix multiple acids, again, so basically all this is saying is that the strongest acid, whatever weak acid it is, that strongest version it is, will contribute the greatest hydrogen concentration, and so it's the only thing we need to take into account. Okay, so you can disregard the other acids that are in that solution. All right? That's all I need to say for that. Now, this very last thing is going to be the calculation of pH with a polyprotic acid. So basically, this is going to take a little bit of last lesson and the lesson for today and kind of combine it. Basically, we know that a polyprotic acid is going to be an acid that's got more than one hydrogen in it. And what we have to do is we have to dissociate it stepwise. And all that means is that each hydrogen is going to be removed one at a time. For example, sulfuric acid, that's H2SO4, it's got 2 hydrogens there to work with. And so we remove one hydrogen at a time when we're removing it from, for determining that pH or for determining our values in terms of that, okay? So that being said, with us removing it one at a time, we're going to have to calculate those concentrations as we remove those individuals. Now, H2SO4 is the only acid, the only polyprotic acid that you actually need to worry about the consecutive hydrogens being removed. Why? Because as we remove a hydrogen, we know that we're going to have such a diminishing value. It's going to take so much more for that to actually remove a hydrogen that we won't actually see that big of an effect. We're going to make the assumption that those further stepwise, those further hydrogens being removed are going to have so little effect that they don't matter. And so basically the second and third and fourth and whatever, we can ignore those hydrogens being removed. Again, the exception to that is sulfuric acid. Why? Because it is a strong acid. So we do need to take into account both the strong acid part of it and then the weak acid when it is dissociating. All right. Now, this is going to be a little bit of both. So basically what I want y'all to do is to go ahead and give this a try. Now, you are going to actually have to use the quadratic equation on this. And so this is a bit of a challenge problem for you. So I want you to go ahead and try to work it out. One thing to remember is that you do have the strong acid, which remember it completely dissociates. And you have the weak acid, which you're going to have to take that into account. Add those two values together, okay? So pause your video, try to solve this. If you can't, that's okay. I am going to go over it, but pause your video, try to solve it, and then we'll talk about it. All right, so here we go. So again, remember that with a strong acid, we do make the assumption that that first hydrogen ion is going to be completely dissociated, right? And so the first dissociation, its concentration is going to equal the concentration of the solution. So 1.00 times 10 to the negative 2. Now, I need to solve for that next hydrogen that is going to be removed, but it is no longer a strong acid, so we can't assume 100% dissociation. So it's a weak acid, so we're going to have to use our Rice table. And so that is what I did next here. So I solved for my Rice table. Now, one thing to note here is that my hydrogen ion concentration is already going to have some hydrogen there. Why? Because it completely dissociated with that first hydrogen being removed from that polyprotic acid. Okay. So again, I made that assumption. I plugged in my values. I wrote my Ka expression, and I went ahead and solved for that. Now, again, if you notice, this is not really something that we can solve here. So what we're going to have to do is actually plug this into our quadratic equation. And so that is what I did here. And I did use 0.22, or sorry, it shouldn't be 0.22. This needs to be erased. It should be 2.2 times 10 to the negative 2, right there. And then we did plus or minus. And we got this right here. We plugged it in, and what we found is that we could have gotten an answer of either 0.027 or 4.5 times 10 to the negative 3. Okay, so I chose the 4.5 times 10 to the negative 3 because it is a positive value. We're not going to have a negative concentration here. So what I found is that my second dissociation was 4.5 times 10 to the negative 3. Well, now I've got my first dissociation, which was 1.00 times 10 to the negative 2. And I've got my second dissociation, which was 4.5 times 10 to the negative 3. I add those two values, and I have my final hydrogen concentration. Now I need to solve for my pH. So pH equals the negative log of those two values getting added together. And I found that my pH equaled 1.84. Now, again, this does have the quadratic equation on it, and so you would not be asked this on the AP test, but they might ask you a conceptual question in terms of, well, what do I do if I've got, a strong acid that is a polyprotic strong acid? How would I determine that pH? Okay, and so do keep that in mind. I did want y'all to kind of work through this and do your best to solve it, but that is it for this set of notes. As always, let us know if you've got any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.